It's a particular pleasure to be here today and share with you the most recent developments in the photovoltaic space within DuPont. A lot is happening here in the Valley, but also at Stanford. So it's an opportunity for us to share with you our company and what we have been doing in this area of renewable energy. So I would like to introduce DuPont, the company, but focus more on the energy story. I will touch a little bit on the energy storage, but primarily my presentation will focus on photovoltaics. And then I will talk about our key products, the metallization paste, the backsheets, encapsulants, as well as other structural materials, and then the very future view of our PV innovations. So who is DuPont? DuPont has been around for a long time. We are a science company. We work collaboratively to find sustainable, innovative, market-driven solutions to solve some of the world's biggest challenges, making lives better, safer, and healthier for people everywhere. I'll give you a timeline of the history of DuPont. DuPont is a 213-year company. It was established very early in the 1800s with a family of DuPont that came over after the French Revolution and started the business with explosives, gunpowder. For more than 100 years, DuPont worked in this area and worked very closely with the American government. And at the early of the 1900s, they diversified. They went into dyes. And of course, were the first ones to discover polymers, plastics, and names that we see on our everyday life, starting with rayon, nylon, and a little bit later, you can see some of the well-known names there, like Corian, Kevlar, Tyvek, brand names that you see while you're driving around, things that you use on your everyday life. And most recently, the innovation and the science has merged into bringing together different parts of chemistry and biology by delivering more complex solutions. And you can see there that the company has gone into agriculture, nutrition, and bioscience. We have acquired companies, but also we're in the process of separating for certain businesses like the paints business and the performance chemicals that will be completed this June. So going forward, the three foundations of our business is based on agriculture and nutrition. This is a huge growth area. Industrial bioscience, with the acquisition of Genenco down the street, and the traditional business that revolves around advanced materials. So I will be talking about this with emphasis on photovoltaics. So let's talk a little bit about the DuPont energy story and why this is so important for DuPont. So there is a science to energy secure future, conserving today's resources while developing the cleaner alternatives of tomorrow. So science-based innovations will help make our consumption of valuable energy resources more efficient. But at the same time, they will have to be more reliable so we can bring balance with the energy supply out there. And of course, at the same time, they have to be economically feasible and environmentally sound. But we cannot do this without collaboration between the scientists, the policy, the community, and the private sectors. And in the bottom there of the slide, you can see all the different businesses that DuPont is focusing on, all the way from automotive, biofuels, biomaterials, building and construction. I will talk today a lot about photovoltaics, a little bit about storage, and of course, a new area of lightweight materials. So in the area of storage, we have already three areas of focus within our company. We want to make the cars more efficient and more environmentally friendly. So this is an area where our energy storage improvements will help tremendously in the near future. But also we have a strong tradition in consumer electronics. These are obvious. Of course, we want to make the handheld devices more last longer, so we can use brighter displays, so we can be on them without needing a charging for a long time. So, and at the same time, make the photovoltaic solutions more sustainable in a way that you don't have intermittent power generation. So the stores can work together with the photovoltaic panels in a way that you have continuous power generation. So these are the three areas that are driving our energy storage activity. And we're going to go after particularly the energy density. And how we're going to do this? We will do this by offering material solutions that deliver higher voltage systems. Higher voltage electrolytes, binders, but also materials that improve the electrodes, interfaces, as well as durable behavior of charge and ionic transport. And we will do this thing by working with value chain partners, from one hand, but also battery manufacturers on the other. And we will be, in a sense, the materials provider, the materials solution for this new business for us. So let me start a little bit now talking about photovoltaics, and my presentation will be focused on photovoltaics. This is the area that I've been spending most of my time. What you see there is the growth of photovoltaics, the demand out there, since 2009, starting with a little bit more than 5 gigawatts. Just to give you an idea, this is how much power US will install this year. And all the way down to 2018, we're going to go up 10 times. Now, if you go all the way up to, down to 2000, the demand was a lot less than a gigawatt. So we have seen tremendous growth. And how this thing has been achieved? It has been achieved primarily with innovation in crystalline silicon. More than 90% of the PV panels today, and also in the next 5 years, will be primarily made out of crystalline silicon. A very successful story, a very sustainable story. So what we show there is the cross-section of a traditional PV panel. We have expanded the view so you can see the different parts of the panel. If you turn around here across the roof, you will see panels of that sort. Of course, you see here the crystalline silicon wafers. DuPont provides the metallization materials that extract the current from these cells. But also we make the encapsulants that protect the cells. And the backsheet that you see there is also a DuPont material. And finally, the structural materials that you see for making the junction box, as well as the frame, can be done by using polymer materials. And finally, the doping materials for helping you to form the junctions in the cell. So diving deeper into the product line of DuPont, we have developed this history as a specialty materials supplier for the solar industry for more than 30 years. As a matter of fact, our PV materials are out there in the field for 40 years or so. We were one of the first to introduce the metallization materials. This is silver paste that is used, as I said, to extract the current from the cell, and I will talk more about this. The Tedlar polymer films are part of the backsheets that is used to protect the module, to isolate it electrically and environmentally from the environment. And then the encapsulants, we started with EVA and now we're merging into ionomers, are protecting the cells from the environment. And finally, a new area of growth that we're learning actually from our automotive business is the area of structural polymers. How can we replace metal? And with components that will speed up the installation cost and bring the cost of the modules down. So there are three things that you need to remember: that this type of advanced materials improve the power output, they improve the reliability, and of course, they deliver the best possible return on your investment. I have a series of photos to share with you. What you see there, it's a snapshot of the tool that we are making, this paste material. There is more than 80 years of history of how to make this paste, but only recently we have learned how to refine the material so it can deliver the highest possible current and the highest possible power that can be extracted from the cells. This is a photo of a production line of the backsheet. The Tedlar polymer provides excellent protection from the environment, has been around for more than 30 years, and it has a proven history. And of course, we work with partners that make the backsheets, and then the module integrators will laminate the backsheet on the rear side of the module for providing this protection. And how do we achieve this? With very strong R&D and strong innovation programs. Down the street, we have the ability to make not only cells, but also modules under one roof. We have learned early on to make state-of-the-art crystalline silicon solar cells, and at the same time, transfer them into a module assembly line so we understand better how the materials at the cell level interact with the materials at the module level, and then go back to the design phase to improve the performance in terms of power, efficiency, etc. So this is one of the unique assets that we have in our inventory that helps us to design the best possible materials. Most of you that are dealing with photovoltaics know that those three pillars, the foundation pillars of photovoltaics, are extremely important for succeeding in this field. When you design a new system, when you design a new materials solution for photovoltaics, you want to make sure that what you're delivering, it will be efficient, but at the same time, it will have an attractive cost of ownership. And finally, you will deliver a lifetime at the module level that will be at least 25 years. Now, those three pillars are inseparable. You cannot work on two and ignore the other. All those three need to work hand in hand for delivering the best possible solution. And that has become a lot more important as we develop the new products and the new material solutions going forward. What you see there is the progress in cell efficiency, crystalline silicon cell efficiency, the past 5 or 6 years, based on the front side silver paste. It's something that most of the industry doesn't know, but the majority of the progress in cell efficiency, we started around 18% at the cell level, and now we are at 19.5. Primarily, this progress has come as a result of tuning the silver paste in conjunction with the doping concentration of the phosphorus on the top surface of the crystalline silicon. And I will say a few words of how we do this. The first jump took place with the product PV17X. We were the first ones to pioneer this substantial gain. I have to explain to you that every 0.1, although it sounds very low, it's a huge progress in the industry. It provides a huge differentiation for those that are capable of producing cells with this extra efficiency. It differentiates the product. And it's a great differentiator for power. Of course, you need to do this thing making sure that you don't compromise manufacturing cost and reliability. So around 2011, we'll deliver this type of products. And most recently, we're introducing, actually, a few months ago, we introduced the PV19. And the beauty of this product is that it can deliver very fine lines. And why we care about fine lines, the important thing there is that you don't want to shade the light. You want to minimize the footprint of the silver on the front surface. So 10 years ago, we used to use about 400 milligrams of silver on the front surface. That, in combination with a very high price of silver, used to be a dark cloud on everybody's mind. And we have worked closely with our customers to reduce, as we call it, the lay down from 400 down to 100 pretty much the past 10 years. Silver used to be one of the most expensive materials components in crystalline silicon panels, and now it's not. The frame, for instance, or the glass is more expensive than the silver. And that came as a result of strong innovation within DuPont, but also a strong relation with our customers. Jointly, we managed to bring down the cost of ownership as well as the performance of the cells. And at the same time, you see how the power in power density is going up and continues to go up as a result of this fine-tuning of the metallization that we're making. Some of you may recall that the cells used to be 5-inch squares or pseudo-squares, and now they're 6. They used to have 2 bus bars, and now they have 3 bus bars, and eventually they will have 4 and 5. And although you are increasing the number of lines, you are reducing the silver as well as the shading, which is 5 or 10 years ago was almost impossible to conceive. But again, innovation has delivered this solution. So some of the hard problems that we're trying to solve is learn how, what you can see there is the cross-section of the silver. Imagine that you have these finger silver lines on the crystalline silicon, and the silver tends to spread, and the more it spreads, the more it will shade the light. So what you want to do is have very tall silver lines and very narrow lines, and have many of them. So what we have achieved, although it sounds trivial, it's a very hard problem to do. We have been able, the past year or two, to narrow the width of the silver by 10 or so microns. And we have done this by working closely between the screen technology, the paste formulation, and of course, different pattern designs of the cell. So what we were able to achieve since 2010, we went from 80 microns at the screen level, going down to 30. These are huge changes in the design. 10 years ago, we thought that screen printing is not capable of delivering this fine line. But we believe that screen printing can go even lower than 30 microns, all the way down to 25 or 20 one day. And we do this with careful chemical engineering and science by working out the formulation in a way that when you print it on the crystalline silicon wafer, it stays put in place, it doesn't spread, and at the same time has very good adhesion and very good conductivity. Almost similar to the conductivity of bulk silver. So what happens with the designs, with the crystalline silicon designs? As of today, the majority of the industry has been using a very traditional design where finger lines are going on top and a blanket of aluminum paste is screen printed in the rear. Now, this device structure has been extremely successful, and more than 95% of the crystalline silicon panels out there follow this design. It's very reliable, but it has some limitations. The aluminum that you have in the rear contributes in a negative way towards the recombination, to use a technical term, for the positive and negative carriers in the cell. So what the industry is doing today is to passivate the rear side the same way we have been passivating the front side with silicon nitride. Now we also passivate the rear side with silicon nitride and aluminum oxide, and then we drill holes for allowing the aluminum, specially designed aluminum, to selectively contact the rear. Only 5% of the area is contacted. So that gives you superior performance in the rear, and you have efficiency improvement. So you can see that you can go from 19.5 all the way up to 21 plus with this device architecture. And of course, the ultimate device structure, a device structure that has been pioneered by the group here in Stanford and then commercialized by SunPower, is the all-back contacted cell. And this is the ultimate cell that can deliver the highest efficiency in crystalline silicon. We are listing here 22 to 24, but efficiencies well above that are also possible. Of course, as you go from this device structure to this and then to IBC, the complexity increases tremendously. So the reason that the industry is not rushing through this is because we don't yet know how to mass produce these structures in a cost-effective way with materials that can deliver an attractive cost of ownership. So we talked about efficiency. At the same time, we care a lot about reliability. And because we have access to at least 3 different materials that make the module, we have launched a holistic cell and module reliability program where we look at the interactions of the materials as it's related to their durability. And of course, the only way that you can do this thing in a way that you can solve problems is to understand the science behind that. And then you go back to the drawing board, design the materials in a way that can deliver more reliable performance. I talked about the Tedlar. The Tedlar-based backsheets is the only solution out there that has been in the field for more than 40 years. We have a proven history. And of course, this is a great area to be. And for that, there are a lot of different approaches. Many different polymers can provide backsheets, but they don't have the track record that Tedlar has. Just keep in mind that the minimum warranty that you need for your modules is 20 years. And we have examples where Tedlar has been used out in the field for more than 30 years, where what you see there with the acronyms are different classes of polymers that provide backside protection, but they don't have the track record as Tedlar. And these are photos of panels and fields that use DuPont materials backsheets. You can see here from a photo from a 10 kilowatt site in Switzerland where Tedlar film-based backsheets are used and the panels still are fully functional. You can see the installation was done in 1982. That's another example, not very far from here, where both Tedlar and Solamet has been used. We were pretty much the only one at that time that could provide these solutions. This installation was, I would say, the first US utility installation, and it's still in full operation and delivers successfully power. So that's a strong reaffirmation that, that this technology is very reliable. And of course, crystalline silicon is the story behind this. But of course, the materials protect the operation of the module and the cells. And we do this thing with our approaches. The other area that we're looking into, and we're starting to interact with Stanford in this area, is to understand how the ribbons attach to the bus bars and how the metal fingers that I was talking earlier perform under aggressive testing environments. It's very important to adhere the ribbons that collect the current very nicely on the cells, but at the same time, if different environmental conditions can corrode the silver fingers, delaminate them, and eventually kill the device after prolonged exposure to different environmental conditions. So we look at how strong is the adhesion on the cell. It's very important, and Stanford is an expert on adhesion, and we are starting a program in this area with Professor Daushardt. But also we're looking what happens with the acids and the other chemicals that there are byproducts of water penetration. Do the fingers laminate or not? These are areas that we need to understand very well. And of course, everything is related to the encapsulants. So we're moving into a new class of encapsulants, ionomer-based encapsulants that will address some of these issues. Some of the biggest problems today in the industry revolve around potentially induced degradation that has to do with the sodium from the glass that penetrates through the encapsulant and then attacks the ions, attack the cell. So we need to stop the migration of the sodium ions, and we do this thing with ionomer-type encapsulants. At the same time, cracks, microcracks in the cells, as the cells get thinner and thinner, they're prone to cracking. Today's modules employ cells that are close to 200 microns or 180 microns. And you can crack them very easily. So water that permeates through these cracks interacts with the encapsulant, creates acids, and those acids attack the silver. So you want to use encapsulants that don't have byproducts of that sort. And the ionomers actually have proven to provide this great protection. And finally, the product that we most recently introduced, particularly for flat roofs and roofs that cannot sustain penetration. What you see there are mounts made out of plastic material, composite material that we have designed specifically for automotive, but now we're transferring this know-how into photovoltaics. The panels rest on these pedestals, these mounts, on flat surfaces in a way that you don't have to penetrate the roof, in a way that they are pretty solid and resistant to wind and provide great UV weathering performance. And of course, they're lightweight. So I would like to end my presentation by highlighting some of our future activities within our research departments. We have actually a collaboration here with Stanford in the area of perovskites. Of course, what has attracted our attention is the very rapid progress in the efficiency and the potential of making roll-to-roll PVs having efficiencies above 20%. This is huge in the industry. And let me wrap up by sharing with you our long-term vision. We have programs that are looking into lightweight panels that are glass-free. Can we replace glass with an organic polymer type material? Can we have crystalline silicon wafers that are flexible, that we can deliver wrap-around, high-efficiency panels? And then eventually, do we have a material system that can be processed in a roll-to-roll fashion to bring the manufacturing cost down without, of course, affecting the reliability? So I would like to end with my summary. I hope I have convinced you that the materials matter in photovoltaics, and materials are a key determinant for module performance. We talked about the metallization and the importance of metallization in the efficiency of the modules. The Tedlar film-based backsheets and how important they are in protecting the PV panels and the history that we have behind them, the field-proven history. The ionomers and the polymer composites, and finally, I share with you my long-term vision in photovoltaics. And with that, I would like to thank you very much for your attention. All right. Thank you.
Thank you. There's time for a couple of questions. And Marjorie has a microphone in the back of the room. There's another one over there, too, in case anyone would like to ask a question to Homer.
Very good talk. In your slide comparing the materials, you didn't include the 3.5s. Is some reason for that?
Yes. I list, in my mind, 3.5s as a future technology. And again, to enable a new PV technology as a real solution, you need to make sure that all three pillars are met. Efficiency, we have that with 3.5s. Reliability, we have that. But the cost is an area that 3.5s needs to continue to work on. Right now, the 3.5 material solution, it's not compatible with the cost requirements for photovoltaics. So we need to bring 3.5's processability down to the processability of crystalline silicon. Then I believe they have the future. Of course, the higher efficiency, the 20, 30% higher efficiency can compensate, so they can afford to be a little bit more expensive, but not factors of 5 or 10. That's why.
Thank you.
Okay, I think we'll take one more question. We have to proceed here. One more up at the front. Yeah.
You had a lot of discussion about the efficiency. Do you see any degradation of efficiency as a function of time? And has that been studied?
Of course.
Yeah.
It has been studied thoroughly, particularly in the area of crystalline silicon. What is desirable is to have about 0.5% loss per year for the crystalline silicon panels. And of course, at the end of life, 25 years or so, you don't want to be below 80% of the maximum. So even after 25 years, the panel will continue to operate. Now, of course, the lifetime is extremely important because it's directly linked to your investment. The slower the degradation, the higher the return on your investment. So you want to be aiming at better than or equal to 0.5% annually, not more.
So I misspoke a moment ago. We have time for one more question. So if somebody has that question, and I apologize for cutting them off. Yeah, I think there's one back there.
Hi, Craig Lewis with the Clean Coalition. Wonderful presentation, Homer. Thank you, and congratulations on such a tremendous portfolio. You kind of finished with a comment about the reel-to-reel, and you know, I see that as kind of the nirvana if we can get that to a high reliability manufacturing process and you know, have all the benefits of long lifetime and whatnot and cost effectiveness. Where do you see that kind of in its state toward hitting that objective, that overall, you know, end performance?
Good question. You call it nirvana, I call it holy grail. It's a good way to end the presentation, first of all. It's a hard problem to address, and this is something that universities like Stanford can more seriously look into. It's not an easy proposition. You need to be able to do all materials in a roll-to-roll or reel-to-reel fashion, not only the absorber, but also the conductors, right? And in order to utilize the high throughput cost advantage, you need to finish the module in a reel-to-reel fashion so you can enjoy manufacturing costs all the way down to 20 cents a watt or something like that. Unfortunately, we don't have yet all these components finalized and fully developed. And at the same time, we don't have a large number of absorbers that can be dealt in a roll-to-roll fashion. So a lot more work is required. You see, I didn't put a timeline there. It will take a substantial amount of R&D to deliver roll-to-roll manufacturing. This is not something that will happen next year or the year after. Now, there are companies that are doing this, but to deliver a 25-year or 30-year reliable product, it's going to take time, right?
The First Solar approach, right? They're just doing panel by panel, I think, but it's pretty much a set process from right, materials in, panels out.
Correct. That's the other approach where you have an inline or a batch process where it can also deliver a very attractive manufacturing cost, right? As a matter of fact, there are many industries out there in the optoelectronics world that they're processing devices in a high throughput mode that can be very attractive. So the whole idea of the reel-to-reel, the roll-to-roll is to take the manufacturing cost without affecting efficiency and reliability down to very low levels. So instead of having, let's say, a meter square per minute throughput, you increase this by a factor of 10 or even 100, right? So basically, you want to make PV panels like the printing press. Only then you have a value proposition, because you have all these competing, already existing glass-to-glass assembly lines that work very efficiently today.
All right, well, let's thank Homer for an excellent keynote presentation.
All right.